Okay, it should come through any moment. And all right, there we go. Okay, so thank you, ladies and gentlemen. So we were working on linked lists. So linked lists, as we said, were different from arrays and other linear containers. I won't be able to really deal with Discord at the moment. With arrays and other linear containers at the moment, because they don't store their data contiguously. They store it spread throughout the free store, with each data item allocated its own block of memory that contains at least enough space for that data item itself and a link to the next item in the chain. And then basically by following the links from the first element to the final element, which is called the tail, which will link to null, you're able to access all the elements in the sequence, even though they're not next to each other in memory. So you can't index into a linked list. That doesn't make sense, because indexing relies on jumping to the start location and then exploiting the fact that the data is contiguous to jump forward immediately to the item you want, which doesn't make sense because you don't know where in memory the next item is going to be. Could be in front of you, could be behind you, could be far away, could be nearby, you don't know. The only way to know is to follow the link. You could create a fake index, which would basically just repeatedly follow the links as many times as the index said. So you can create an indexing operator to a linked list, no problem, but it'll be slow because it'll have to follow the chains. It won't be real indexing, at least in the same way that an array is. We started implementing a basic linked list, and we'll continue with that. But I just want to cover the next little bit of theory, and we'll also do implementations of linked lists in the tutorials as well, because it is in your exam, even though it's not in the practical test. It still it's still examinable work. And then also regarding Prac 9, of course, with this Friday being the informatics semester test, there is no practical, and the following being the final one. We can't have something that needs time to mark due on the last day. So the linked list practical assessment will take the form of an extra VPL assignment. So it'll just go into the same pool of VPL assignments. So I'd advise doing it because revision for semester for exam, but it's in the same pool of supplementary exercises. That'll be up sometime this week, due at the end of next week. All right, so let's continue. All right, so yeah, we saw what the basic operations were. We actually really started implementing these. I think we had, let's take a look, basic. Let's see what we had. We made it templated because as a general container, that is a desirable thing. We had the ability to insert first and last. I don't think we'd implemented both of them. We just implemented insert last, which I think we got working. Yeah, seems to be fine. So we're able to create our linked list, and the copying all seems to work. We can reduce the noise of our debugging statements at the moment. Don't need that much output. And our destructs as well also works. So a lot of these operations, as we saw, are built on the basic traversal, which starts at the first node and then follows the links until it hits null, as we've seen. So let's get our copy constructor and just quiet it down as well. I think that's in main. If it's in main, then we can leave it. All right, so don't know why I'm outputting to see error. That's not really an error. It should be debugging. That's not really an error. Okay. And so yeah, we can implement inserting at the beginning, as well as searching for a particular value, as well as we've actually done most of the rest. Then I think just inserting after an existing item or deleting after an existing item are things that we could also potentially want to do. So that's fine. But let's just take a look at what else we can do once we've got our linked list finished up, is to implement an iterator. So an iterator is a kind of smart pointer. So what is a smart pointer? Well, okay, that's not true. An iterator is a construct that allows you to access all of the elements in a container in some kind of a sequence. So it gives you one at a time access to each element in the container. In C++, because the traditional way to access elements in an array was to do pointer arithmetic to move from the first element to the last to the next element until you get to the last one. The convention for providing such access to a collection in C++ is to make it look and feel like a pointer. You can't just use a regular pointer and regular pointer arithmetic because the values aren't contiguous. So what we do is we create a class that implements the operators we expect from a pointer, except it modifies their behavior to instead follow the links in the linked list rather than rely on each element being contiguous in memory. So because it implements the functionality of a pointer and feels like a pointer, it's a kind of smart pointer. And then just as a quick aside, for smart pointers in C++, they're actually quite useful in real production programming. So there's a whole bunch of smart pointers that exist and come with the language. We can take a bit of a look at them once we finish the main content of the theory. The main job of a smart pointer in modern C++ programming is to free you from the need to remember to delete your pointers at the end of the day. So basically it's just a class that has your pointer for you and then implements the destructor to delete it when it goes out of scope, or if it's there's a bunch of things that could all be pointing to the same thing. The last one to let go of it will delete it. That's called a shared pointer. So the two types are in main use now are standard unique pointer and standard shared pointer. There is a variant of the shared pointer you can create called a weak pointer that doesn't actually increment the count of how many things are sharing this thing. It's kind of the equivalent of a reference rather than a pointer, but it's not as widely used. But basically the two main ones that get used are a unique pointer, where you have a single thing that owns the memory that you've allocated, and it will delete it automatically when it goes out of scope. And the other thing is the shared pointer, where it keeps account of everyone that's currently pointing to that particular place in memory via shared pointers. Obviously, you can do that through a static class variable, and then when the last one drops, and every time you add one, it increments. Every time you one goes out of scope, the destructor will first check, is there anyone else sharing? If not, delete the thing and decrement the count, and if not, then just decrement the count. And basically that gives you an easier way to deal with memory and a safer way to deal with memory than raw pointers. And raw pointers, we force you to use them because it's good practice, because it's resource management, and pointers aren't the only kind of resource that exist that need to be acquired, used, and released. As you've seen, you've already got files that follow that pattern, and in future you'll deal with things like database connections, network connections, which all need to be managed. So it's good practice to learn to remember to allocate, use, deallocate, and not just rely on the built-in mechanisms that do it for you. It's also why, while we use vectors, we force you to use a dynamic raw array in your data types to give you that practice. All right, so official practice. There's nothing unofficial about a VPL, but there can't be a full practical session because it's the semester test this Friday for informatics. So because they're shared students, we can't have one. Please, please, please read the notices on Eve. The SIG test for semester test 2. A, it's in the learning guide, which you've had since the beginning of the semester, and B, there's a notice on Eve with the application link, and it's been there for 2 days already. So please check notices on Eve. Will we do revision for the exam as with the semester test? Yes, we will. Even what we probably will wind up doing is after the official end of the class, we might still wind up uploading pre-recorded revision sessions and so on, and we'll probably have some intensive revision things as well. So we'll do it in class. There's not much left to do, and then we will do revision for sure. This is absolutely untrue. If you wrote semester 2, you may not apply for the supplementary. It's only for those who could not write due to some reason outside of their control. It's a sick test and an ergotat, strictly speaking. If you've got some medical proof that you wrote, but you had something that prevented you from writing fully, and you've got a medical certificate for it, then obviously you can apply. But you need that ironclad certificate. An affidavit won't be enough if you've written already. You'd need to get some sort of concrete proof that you could need to write again. So no, it's not a retest or an extra test. It's a sick test and a substitute test for people who didn't write. So strictly speaking, it's an SA test, but the term the university uses is SSA. All right. All right. So that's what the most common kind of shared pointers are in practice in modern C++. You basically just use them like any templated type. We can do some examples with them. So you'd have a unique pointer of, let's say, a student, which rather than a student pointer, and rather than having to remember to delete it as soon as this goes out of scope, it will delete the pointer for you. So there's a make pointer or make unique function that will create the pointer for you. And then inside this, you put the raw pointer, so new student, and then you just forget about it. You just use it as if it were a regular pointer. So all of the dereferencing and arrow operators are overloaded for it, except that when it goes out of scope, it'll delete the student for you, so you never have to remember, like you would here. Remember to delete P, because this does it for you. You could easily create your own unique pointer data type with everything you know so far, because all it's basically built up of is a templated type. We can see that. It has a destructor that will delete the thing that comes in. So you can see that this make unique function would have a well, in this case, it would have to be a fairly general one, so like a templated pointer of type T coming in, and then inside the destructor it deletes it, and then they overload the asterisk operator, assignment, comparison, the arrow operator, and that's about all they would really need to overload, and then you pretend it's a pointer. So I don't know, whatever's in a student, student number and a mark, for example, and yeah, just you don't have to remember to delete it. So they're very, very useful, but iterators are a variant of the idea of a link or of a smart pointer in C++, and their purpose is to give you access to each element of a container one at a time. Because they're smart pointers, they have the increment operator overloaded. That's for a singly linked list, so you can iterate forward through the linked list, and the dereferencing operator that gives you access to each element, so you can do stuff with it, modify it or access it. So it's a class. You'll instantiate it as an object. It's typically very tightly bound to its containing class. So this is one of those cases where it absolutely makes sense to implement all of the things in the same header file. Because to be honest, you're not going to be creating iterators manually. What you're going to do is you're going to ask the linked list, please give me an iterator that points to the beginning of your collection, and or please give me an iterator that points to the end of your collection. So that you can move through the collection using a loop, pretending that they're pointers. So yeah, I think that gets the idea across. So let's, in fact, before we do, okay, that's an excellent question. So with these smart pointers, can we use them to do multi-dimensional arrays? And of course, you can nest them. You can have pointers of smart pointers with smart pointers, just like you can have double or triple pointers or quadruple or however many you want in normal C++. So you can nest them inside each other, just like you can have a vector of vectors. You can have a smart pointer of smart pointers. Not a problem. So you can definitely do that to make your multidimensional arrays, if that's what you wanted to do. Of course, if you used all of these smart things like vectors or smart pointers, then you wouldn't have any reason to practice writing destructors, because everything would take care of itself, or copy constructors, because again everything would take care of itself. So that's why we force you to use raw fixed length arrays, raw dynamic arrays. Anyway, so we think we've got enough functionality to build an iterator for this. We can add more functionality to our linked list as we go forward. So let's do that. So we're going to create our linked list type inside, our iterator type inside the same header file, because let's say they're deeply aligned with each other. Let's call it an iterator. It basically will wrap around the pointer so that we don't have to worry about the node pointer, so we don't have to worry about those details when working with the linked list. So inside it will have a node templated. Inside it will contain a pointer of type t. So just say that that's the node that it points to, and then we need some things like constructors and destructors, and so not destructors, constructors, and the operators for accessing values. It won't own the pointer, so this is an important thing to note. It'll start off pointing to the head of the linked list, and you'll use it to move through the linked list, but its job is not to delete the contents of the linked list. That would break the linked list and be a terrible problem. So this is a very weak kind of a link between the two. It's only going to be an aggregation link in a sense, because there's no ownership of that pointer. It simply gives you access to it, and it's totally fine for this to be null as well, as you'll see. So let's make it simple. Let's just make an args constructor. At bare basics, what do we need? We need the ability to compare our iterator two iterators together in the same way that you'd compare two pointers to each other to see if they point to the same thing, like we do with this and the right-hand side and copy constructors and so on. So we will want to implement a comparison operator. And we will take an iterator of type t as its parameter. We shouldn't modify anything, so we'll make it const. This shouldn't modify me either, so we'll make it const. And then obj right-hand side. Assignment, we wanted equality test. Likewise, you can basically for free get the inequality test if you've implemented equality, so we may as well. And then we want the ability to access the underlying value inside the iterator. So what does the iterator store? It stores the current node we're at, and the actual value is stored inside the node of type t. So when we access the iterator, we want it to feel like accessing a pointer, so we must get back the thing itself. So let's say t. If we want to make it mutable, you can return a t reference, and we're doing the asterisk operator, but not multiplication. So this is the unary version of that. We provide no right-hand side, because we're just doing a single asterisk on ourselves, not putting us in between a left-hand side and a right-hand side. And then we need the ability to move through the linked list. This is a simple singly linked list. So it is going to, if you look at the nodes, they only store a next value or data member. So we're only going to be able to move forward through this linked list. If we had a doubly linked list, we could move backwards, but in this case we can't. So what we're going to do is we're going to make the plus plus operator. It will give back an iterator of type t, and it will call operator plus, and it's going to be the we'll implement both of them just for some revision. Remember, there are two versions of the incrementing operators. There's the thing plus plus, and there's plus plus the thing. We may as well do both, and we differentiate between the two by an unused int parameter that says that this one's going to be the postfix one, and this one is going to be the prefix plus plus, and this one is going to be postfix plus. And I think that's all we basically need for now. There's no management or ownership of this, so I think that's good enough. We could do a weak copy assignment operator, but I'd rather not bring in the assignment operator necessarily, because the rule of three, like all these rules, there are some exceptions. So this would be a case where if you have an assignment operator, you don't actually want a copy constructor or a destructor. Let's just put it in. Well, a copy constructor is fine, but you definitely don't want a destructor. Let's actually do that. Let's have a the reference. Simply copy the pointer, and yeah, I guess we can do an assignment operator, which will also give us back an iterator of type T, and we'll make it operator sign, and iterator of type T, object right hand side. In this case, no destructor. All right, let's implement this and see how it goes. No, we don't need a new file because this is just living inside along with the linked list. But sometimes people do, and we could do it if we wanted to, but I don't think there's a desperate need to. You can actually make the iterator a friend class of the linked list, or even, as some people implemented, as an inner class inside that. But we will stick to just two closely related classes in the same header file. So we need our type name. Okay, it's not going to be part of the linked list. It's going to be part of the iterator. T. Confuse it with the C++ iterators, which are lowercase. Okay. And that's not right. Okay. And various operators for dereferencing, forward traversal of two, and both kinds of those. Okay. All right. Okay, we should be good. All right, let's do, well, it's not going to really be that complicated. So when we start off the iterator, what is it pointing to? It's pointing to nothing. So mostly it'll be used by the linked list, and the correct pointer will be set via, oh, we don't have a fully qualified constructor. Let's do that. It'll mostly be used by sending this through the node that we wanted to point to. But we'll provide a no-args constructor. In fact, we will find a use for it. The default will then just be that our node is null. And likewise over here, when we're bringing the node in, don't really do much. We simply assign it. Okay if it's null, it's really not a problem. Because our job is just to be like the pointer. The other person who's using us can tell us whether it makes sense for this to be null or not at that point in time. For our copy constructor, we simply want to have a copy of the object originals node. So we don't want to just blindly point to the same. We're okay with blindly pointing to the same thing. It's very simple. So we just set ourselves to equal to obj node. Since we don't own it, we're not going to destroy it when we go out of scope, so it's not a problem. We will simply point to their node. That's fine. For assignments as well, we simply make our node equal to right-hand side's node. Comparison, two iterators are the same if they point to the same place in memory. So we simply return if our node is equal to object right-hand side's node. We can simply repeat that and change that to a not equal to, or we could be fancy and simply return returning, let's use our own. Compare ourselves to the right-hand side. Is this even easier? I don't know. We use this and set equal to not. Because this is so simple, I think the shortcut is actually longer than simply copying and pasting that and changing that to a not equal to. But normally your comparisons will be fairly complicated in other classes, requiring you to loop through things and do all sorts of comparisons. So it would make sense to sort of skip that and to reuse the existing functionality. In this case, because this is simple, I really don't think it really is that helpful. Now, when we dereference a pointer, we get hold of the value. So if we dereference an iterator, we should get hold of the value that's inside the node we're pointing to. So we simply return our node and access its, I think we called it data. In this case, data, yeah. So we access its data. And then because we're returning that by reference, the person can change it or do whatever it is they want with it. And then we've got the two kinds of operators, the pre and post increment. Let's just remind ourselves of their logic. So the first one, the one without the parameter, that's pre-increment. So that's plus plus the thing. That means the change must happen first, and the newly changed value must be returned. So in this case, we're going to follow our pointer, but it doesn't make sense to follow a null. If we're at null, we're kind of stuck. So we can either raise an error, or you can just do nothing. So we're going to say, in this case, we'll just have no effect if we're already null. So if our node not equal to null, then we can move, and we move by doing the standard traversal operation, which is to set node equal to node's successor, which we call next. Otherwise, no effect. But we need to return something, so we need to return the modified value. So we've already modified ourselves, so you can simply return ourselves. Be fine. And over here, what do we need? So if it's the thing plus plus, what happens is we get the old value back, and then the change happens. So what we need to do is we need to back up the old value, so we can make for ourselves an iterator based on, or let's say based on our old value. Then we make the change, just like we did over here, but again, only if it's safe to do so. And then we can return the old one that we backed up in the first step. So return. And we should be good to go. Let's just check if there are any questions before we implement and test. It's called the dereferencing operator, or just the asterisk. I mean, normally 99% of the time you're using it to create a smart pointer-like thing, so you're using it to dereference stuff. But strictly speaking, it's not incorrect to say. If you're using it for other purposes, it would be confusing to call it the dereferencing operator. So in this context, we're using it to create a smart pointer. Smart pointers get dereferenced, so the asterisk operator is the dereferencing operator. But yeah, in more generally, it's just an asterisk. There might be other terms for it though. One thing, yeah, but those are the two I've encountered most commonly. Strictly speaking, the unary asterisk operator, because obviously multiplication would be the binary asterisk operator. Anyway, let's test this, see if we've made any mistakes. We've got our main. Remember, this being a templated class, oopsie, this being a templated class, you're only going to see your error messages once you're using the thing, triggering it to be compiled. So here we go. We've inserted things into our linked list. We've printed our linked list. We've tested the copy constructor. I haven't really tested assignment. We should probably do that at some point. But what we do need to do, if we're going to now play with the iterator, we need a way to access the iterators. So we need to modify our linked list itself to return iterators to the beginning and the end of our list. So exactly what we're going to do. And the standard names for those functions are begin and end. And begin will return an iterator pointing to your head. And then a little bit confusingly, tail conventionally doesn't actually, end doesn't return an iterator pointing to tail, but rather to the literal end of your linked list, which in this case is the final null after tail. Don't ask me why that became the convention, but it definitely is. I suppose it does make using it in a loop easier, as we'll see now. In fact, that's probably exactly why it became the convention. But yeah, so it doesn't return, as counterintuitive as it seems, end doesn't return a pointer to tail. It returns an iterator tail. It returns one to the null after tail, because that's the real end of your list. Obviously, if your list only has one thing in it, then there's no difference. All right, so let's implement these functions. Let's put them here before the iterator starts. That makes sense. And these belong to the linked list, not to the iterator. Go, and it's very straightforward. If we're returning, let's say to the end, we will return a new iterator of type T to null. And over here, if we are pointing to the beginning of our linked list, we will return an iterator of type T pointing to the head of our linked list. Good. So now we can see whether this works or not. So let's just do a loop where we will loop over our linked list and output its contents. And that should let us test a lot of the things. All right, so here we go. We're going to create a loop. Our loop will be based around an iterator of type T. Call it. And it's going to start off at our linked list. So obj list begin. As long as we haven't reached the end of the linked list, so as long as iterator is not equal to the end of our linked list. And increment our iterator, we will say it plus plus. Doesn't really matter since we're not using the return value. And then inside, we can use our iterator as if it were a pointer. So we can say dereference it and the space, and then at the end, I guess, another end line. All right, so let's see if this compiles. And if we can get that working in the last couple of minutes, then we should be happy. Bleh. Does not like. Right. Okay, yeah, sorry, we're gonna have to move the iterator up. This is one of the consequences of putting things in the same file, as of course order is important, but the iterator needs to know about the node. It doesn't actually literally know about the linked list it's part of, but the linked list now needs to know about the iterator. So that's one thing we can sort out. Okay, you didn't like that. Did I not make a constructor for you that takes in a node? I thought I did. No, I did not. That was foolish. The parameterized constructor, take in a node of type D. Oh, I created one, but I didn't put it in the header file. Okay. Oh, that was my mistake. I made it part of the linked list, not part of the iterator. Let's try again. Oh, of type T. Sorry, this is actually a linked list of type char, so this is going to be of type char. So that should be okay, hopefully. Let's try again. Oh, it's supposed to be a node pointer. And try again. Okay, compiled, that's one thing. Now let's see if it actually works. So we should see, again, just another print out of the contents of the list, this time after the displayed traversing via iterator, and that allows us to use our linked list as our iterators as if it were a pointer. So let's try and see what happens. Run. Yeah, so that works. You see we can access each of the elements in the linked list in sequence as if it were a pointer. Let's see if we can modify values using this. So let's actually, rather than simply outputting the values, let's instead have a, so let's start off with, let's say, capital A. And inside here, we've seen that it's working for extraction. Let's see if it works for modification. We can then set that to ch letter plus plus, and then we've got a print function, so let's just use it. List of opt list, and now we should see the modified capitalized linked list, hopefully. And it does. So you see that we can access our elements, modify them as if we had a pointer. It's not really a pointer, it's wrapping around the pointer and hiding from the users of the linked list the complexity of following the nodes and doing the actual iteration. So you can pretend it's you were doing this using pointer arithmetic. Instead, it actually does the proper traversal for you. So that's the basic idea. I think that's all we really have time for now. So let's just see if there are any other questions. Okay, please explain the arguments in the loop. Perfect, that is a very important question. So we want to loop over the linked list. We can't index into it. There's no indexing in a linked list because it doesn't make sense because the things aren't in any particular order in memory. So we want to access each element one at a time. So we created this begin function that returns an iterator that points to head. the first node in the linked list. We then also created an iterator that points to the end of the linked list. Technically, the end of the linked list is the null that comes after the head. So that's exactly what end does. So what we do is we create an iterator that starts out pointing at the beginning of the linked list. As long as it hasn't reached the end of the linked list, we must keep incrementing it. So then at each point in at each cycle of this loop, IT is going to be pointing to the next element in the linked list, and we can do whatever we want with it. We could output it like we did before, or we could say old value. So we have both examples in the code. And we can modify it, just as if we had a proper pointer to the linked list. So there you see. So that's basically what this means. All right, so that was a really good question. Oh, you use 1 mark. So don't freak out about it. We're not out to get you. That's a 1 mark loss. So if you did it twice, I guess, for the text file and the binary file, then you lose 2 marks, which you could easily make up if you've done some of the bonus. That's why the bonuses are there. So don't panic. Yeah, as I said, we mark according. Well, I didn't say it now, but I said it in Discord. We mark according to a general marking guide rather than a specific memo for one specific way to implement it. So if you've put the stuff in, even if you've made some small mistakes, you're going to get the marks for doing the things we told you to do, like overloading those operators and so on. And even with non-compiling, we'll cap you at the highest mark we're allowed to cap you. So you've still got opportunities to fix the VPL exercises. There are tons of them. So you should be able to, if you've done at least, let's say you did an okay project, but it couldn't compile, it got capped, but it gets capped at a high 40, and then you've done the VPL assignments and you did your practicals, or you just did the VPL assignments to fix your practicals, you'll still be pushed into the 50s and you'll have no problems. It's kind of like an array. So I'm really glad you asked this, because it seems strange. Why do we care? But let's look at this like this. In memory, and an array is literally guaranteed to be next to each other. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. If we allocated these one at a time, though, using mu for each one of these things, there's no guarantee that they would be in any particular order in memory. 1, 2, 3, 4, and then there could be a bunch of other stuff, and then 9, and then a bunch of other stuff, and then 8. There's no guarantee that things are going to be allocated in sequence in memory if we allocate them one at a time. Why would we want to allocate them one at a time? Because often memory is a bit of a mess. Your memory could be filled with all sorts of garbage. And let's just say a value here, value there, and then a gap, and then another value, then a gap, and then more values. And I wanted to allocate a big array. Right, let's say I wanted to allocate an array of size 1, 2, 3, 4, 5. Right? I can't, if my memory looks like this, I can't allocate an array of size 5, even though technically there's enough space in memory for it, because nothing is neatly allocated in memory. It's all just sort of higgledy-piggledy. It's called fragmented. So wouldn't it be nice if we could allocate our data structure so that it wove in between the empty spaces in the, I shouldn't have done that, in between the empty spaces in the linked list. And so if we could still follow from here to there, to there, to there, to there, and use up that space in between everything else, that would be nice. And linked lists let us do that because we follow each link one at a time to the next one, so we can gain access to all the elements at a time. The cost of that is we can't do cheap indexing. We can't say, I'm going to access the second element and just jump straight to it, because that'll get me to the wrong place in memory. But I could follow the link and get there. So if I wanted to access the third element, I'd have to follow once, follow twice, follow thrice, and then get hold of that. So there's a performance cost. They are slower for accessing arbitrary things in the middle of it, but they can weave in between the spaces left by everything else. So that is a benefit. So it's just one more tool in your tool belt. I had an asterisk when it said there was no function matching the class. Why does it not find the function? I can't remember what my exact error was. You'll have to rewatch that bit of my fixing it, but I think I just didn't have a type matching something. I don't actually remember there being a problem with this operator, but so here when I call it in main, and there over there, it finds the corresponding implementation here and simply does the dereferencing and retrieval of the data over there. So I'm not sure which particular area you're referring to, unfortunately. Bad memory assignment. Oops. So if your program crashes because you messed up memory somewhere or another, you'll lose some marks from the algorithm and where you made the mistake. So let's say the mistake was in your constructor. You'll lose marks for that constructor, but nowhere else. So no code, like there's a chain of effects. If you make a mistake, stuff further down the line breaks, but you only lose the marks at the place where you made the mistake. So if that was in a constructor, you'll lose some marks in the constructors, but everything else that depends on that working correctly, you get the full marks for. You must have, look, it's the same compiler under the hood, so I can't give you a general answer there. Because you were making a mistake. Oh, if it was a mistake in memory, then that can very much depend on exactly what happens. So for example, if you're accessing invalid memory, it's not guaranteed to be flagged as invalid every time. So it could just be that the way it was running on the VPL, you weren't crashing, but you were subtly corrupting something, but it didn't cause a crash. Whereas with on VPL running on Windows, the way it happened to be arranged in memory, you caused the crash. So it'd be the same error on both, but it just wasn't triggering the crash on the VPL. Yeah, okay, cool. So is there a certain section which takes up most of the exam? It's fairly even, but thanks for reminding me. I'm going to upload the past papers, so that, and the scope, the structure of them will be the same as the previous years. So one thing we do ask in the theory for the exam, which is pretty big, which we don't force you to do in semester test 2, is the DLLs. So there's a big theory question on DLLs in the exam, which, you know, it's easy if you study it. If you don't, then that's not great. So that might be the one thing which is a bit surprising, but everything else is pretty even. A similar kind of story there. Not every error is going to guarantee to trigger a crash every time, but there will be some reason for it. So every definition will be applied. So instead of asking, give the definition for an abstract data type, we'll describe something to you and you must tell us, is this an abstract data type according to the definition you've learned. So the definitions are there, but they're all applied. You have to know the definition and be able to use it, not just memorize some magic words for marks. Yes, it's very like semester test 1. It's a theory test, remember? Your exam is a theory. It's in your learning guide. It's not a practical. Okay. All right, so we're a bit over time now, so I'm going to stop. I will upload the code we've got so far. It is? It is? It very much is. Is it online? Yes, it will be online. We only have permission to do practical tests on campus. All right, so good question. So go read your learning guide, and you will see. But I'm assuming you're joking. All right, thanks a lot. Have a good afternoon, and see you tomorrow.